So this week we are going to discuss lists, stacks, queues, trees, sets and maps. These all are the abstract data types in C++. Now, what are the abstract data types? An abstract data type is basically a model that defines a data type only by its operations, that what operations you can perform on it, and the behavior of those operations, that what will happen by performing those operations. But how those operations are implemented, it is completely hidden from the user. Just for example, if you're taking an analogy of a car, the interfaces provided to you are the steering wheels, pedals, gear, these. But to drive a car, you do not need to understand that how the engine works, how the transmission works. So you do not need to go into the implementation details. You just use the features provided by it. You just use the behavior and the operations provided by it, but you do not need to take care of that how these operations are implemented. The same way, if you are talking about a mobile phone, to use a mobile phone, we just need to use the operations given by the interface, that you need to press the call button to make a call, you need to you need to tap the red button to disconnect the call and so on. But how these operations are being implemented internally, we do not need to take care about that. So these are the abstraction. So abstract data type is basically that it provides you some of the operations, and or using those operations has some certain behavior, but we do not need to go in detail that how these are implemented. We just use those features. So abstract data type, there are basically two fundamental operating system. There are basically two fundamental object-oriented concepts which we use. That is the encapsulations and information hiding. Encapsulation, that is, we discussed about it earlier also, that you are binding data and methods in a single unit so that we can operate on the data. And information hiding, that is hiding the implementation details from the user. The user just see the interface provided to it, but implementation detail is hidden from the user. In C++, we create this interface and implementation by using two files. One is the header file and one is the implementation file. The header file has the extension of .h or .hpp, which defines that what it will do. It contains all the declaration of methods and it contains all the variables, that what it will do. Now, how those operations will be performed, that is defined in the source file, which has the extension of .cpp. So it contains all the public methods, the interfaces, the definition of the methods which are provided, which user can use. It consists of all the helper methods, the private methods, whereas the .h file contains all the variable declarations and the method declarations. For example, if we discuss an example, this is our .h file, that is, it is the header file which contains only the declaration. This is the .cpp file, implementation file, which contains the definition of methods which are defined here in .h file. And this is our main.cpp, where we are going to use this ADT my class. So we are defining a class my class which has a string name and integer value. We are declaring the constructor, we are declaring the getter and setter for name and value, and we are just declaring a display function. Make sure we are having all the declarations here. We are not defining any function here. Now, In that .cpp file, which is the implementation file, we just define all the functions here. Like we are defining the constructor here, the constructor which is defined over here. We are defining this get name, which is declared here. We are defining it here. Set name, we are defining it here. Get value, we are defining it here. Set value, we are defining here. And display function, we are defining here. So we are defining different functions which are declared in .h file. Now, to use this interface, we are having an interface now. To use this interface in our main file, we will just create an object of my class. That is, we are using our abstract data type, which is my class, and we are calling the method .display. Now, how this .display works, we do not need to bother about. We are not going in detail that how this display method works, because we are given an interface to display the value of object. We need to use this method. So we will just use this method. So the implementation details of this display method is hidden from us. Why the ADTs are important? Why do we use them? First of all, it provides you modularity. Your code is divided into different logical and reusable units, which can be reused. For example, in the last section, we created this my class. Now this my class.h, my class.cpp can be used in any of the program. Maintainability. It is easy to find the bugs now because we are having our code in modules, different modules. We are having different header files, different implementation files. So it is easy to find the bugs and to rectify them. Reusability. A well-designed ADT, like we said, we can define a ADT once and we can use it any number of times in any number of projects. Abstraction, yes, it hides the implementation details, so you can just focus on your logic, that how we need to do it. Like for example, if you need to sort some numbers, you are not going in detail that how to perform the sorting. You just call the function .sort, you just call the interface .sort and it will sort your number. So you just need to focus on your logic. Easier debugging, since you have a defined interface, so you can perform the ADT, test the ADT in isolation. So ADTs are the foundational concepts in computer science and software engineering. They provide abstraction. You just need to focus what to do, not how to do it. In C++, we define the ADTs by using the class templates, public members and interface, and private members of the implementation. Yes, in C++, we have a STL, standard template library. It is the standard template library, which provides us a rich set of highly optimized ADTs implementation. So we can directly use them by using from the STL. So by using the ADTs in your code, you can write a more cleaner, more maintainable code, which is easier to maintain and more robust code. Now let us talk about list and vectors in C++. Okay, before talking about list and vectors, let's talk about a sequence container. A container is something, a sequence container, basically a sequence container is something which is storing the objects of similar type in a linear manner. For example, an array. We all know about arrays. An array holds the data of similar type in a linear ordered sequence. So sequence container is the same, where we are storing the objects of the same time in a linear manner. Now, since the elements are linearly arranged, so each element except the first element and the last element, all the elements has a predecessor and has a successor. Some of the common operations which we use on all of these containers access, if we want to access a particular element at an index, either we can use the square brackets like we use in the arrays, or we can use the dot add function, or we can use a front method which gives us the first element of the container, or we can use the back method which gives us the last element of the container. Iteration, we use iterators on the STL containers which are used to traverse an container. If we need to modify a container, we use insert, dot erase, dot pushback, dot popback. Dot insert to insert an element at a particular location. Dot erase to remove an element at a particular location. Pushback will insert the element at the end. Popback will remove the element from the end. Of these sequence containers, the most usually two containers are std, that is std vector, and std list. So we'll discuss them in detail now. std vector. The vector, there are few limitations with the arrays which we have used till now. They are fixed in size. We cannot increase or decrease the size of arrays. If we need to insert element in between in the array, then we need to perform a lot of shift. Or if we need to delete an element from the array from in between, then we need to shift the elements in the forward direction. So there are some of the limitations of using the arrays. Vectors are a dynamic array. Dynamic array which manages the memory by itself. It's a dynamically allocated array which manages the memory itself. So, like the arrays in vector also, elements are stored in a contiguous memory. Like an array, a vector also can be randomly accessed. That means you can directly access the element at a particular index. So, its complexity is big O of 1. It can reallocate memory by itself when it has to grow, or it can copy and move the elements by itself. So it performs all the memory management itself. Vector. If you're talking about the vector, this is a vector consisting of elements 1, 3, 7, 4, 5. Capacity is the size, number of elements it can hold, whereas the size gives you the number of elements currently are in the vector. Like the arrays, the indexes of vectors also starts with 0. Like, for example, the element 1, it is at index 0, 1, 2, 3, 4. These are the indexes like the arrays. So, the begin, if we are using the iterator, begin will start with element 1 and end will go up to the element 5. Add 2. Either we can use the square brackets in the vector to access the element at a particular index, or we can use the interface, which is the dot at method. So if I give the index dot 2, dot at 2, it will return the element 7, which is at index 2. To use the vector in your code, you need to include the header file dot vector. We need to define a vector of given data type like integer, float, double, char, string. You need to mention the data type, that which type of values it will hold. Now monitor size and capacity. For example, we are going through the values up to 50. So vector.pushback I, we are storing the elements from 0, 1, 2 up to 49. And initially the capacity is 0, right? Every time whenever it needs to grows, the capacity doubles of the initial capacity. So if it is 0, at the first time it will become 1, then from 1 it will be 2, then from 2 it will be 4, then from 4 it will be 8, then from 8 it will be 16, and so on. Capacity doubles every time, and it is done by vector itself. We do not need to worry about. So every time you push the element, push back, that means the element is inserted at the end of the vector. If you print its size, the size will be the current elements stored in the vector, whereas the capacity, the number of elements it can hold now. So initially it can hold 0, then 1, then 2, then 4, 8, 16, and so on. Once it reaches at 64, it will stop because we are storing the 50 elements. So 64 capacity is sufficient to hold the 50 elements. The time complexity, since vectors allows random access, so it is big O of 1. Insertion, removal, all the elements, whether you are performing at a push back or pop back, that is you are performing from the back, it becomes big O of 1. But if you're performing the elements, remove operations, if you're performing the operation in middle, it takes big O of n. Vectors are very efficient, and generally it is a default choice for us for using a sequence. We don't use arrays, we don't use lists, we go for vectors because these are the most efficient data structure in C++. It is random access, so we can use random access. We can perform addition or removal of element at any location. When to avoid it? Whenever you have to perform frequent insertions and deletion. Because if you're performing frequent insertions and deletions in between from the vector, then complexity is big O of n. So it becomes complex. But otherwise, vectors are most, as per me, it is the most useful data structure. Then we talk about the list. STD list basically. So it is a collection of nodes where each node contains an element and pointers to both of the next and previous element. So as we discussed that vectors and arrays are the contiguous memory. So it takes a lot of memory for storing, or we require a big chunk of memory to store the elements. To make it more manageable, we use linked list or doubly linked list in which memories is allocated in terms of nodes. Each node is divided into 3 parts. Each node is divided into 3 parts. One part contains the data which we want to store in the node. One part contains the address of next node. The last part contains the address of next node, and the first part contains the address of previous node. So it becomes something like this. And this portion contains the data which we want to store. Since the first node does not have any predecessor, so it consists a null here. And since the last node does not have a successor, it consists a null to show the termination of linked list. But we do not need to do all these operations by itself. The STD list performs all these operations by itself. We do not need to worry about that how these are implemented because these are done by itself. These are again dynamic in nature because the number of nodes you create. Look, first of all, there is no capacity. There is no capacity because we are not allocating any memory to it. As much nodes are required, this is called a node. as much nodes are required, we create a node at a time. So there is only size, which is the number of nodes, but there is no capacity concept, first of all. Other thing, these are the non-contiguous memory. So memory can be used more efficiently. It is bidirectional iteration. That means you can iterate in forward direction or you can iterate in backward direction, both. And no reallocation is needed. Unlike vectors, where if capacity is reached, we need to double the size every time and moving the data from the previous memory to the new memory. Now here no reallocation is required actually, because every time we need to insert a new node, we will create a just new node in memory, and this will hold the address of this node, this will hold the address of this node, and here it will be null. So we just need to create a node, we just need to remove a node, and we just need to change these pointer assignments. These are the pointers which hold the address of next or previous node. We just need to change these pointer assignments. Lists are sequential in nature. Unlike vectors are random in nature. Lists are sequential in nature. If you want to go to this third node, first of all, you need to go the first node. Then from the first, you need to go to the second node. Then from the second node, you need to go to the third node. So you have to traverse sequentially. You directly cannot go to the node 3. Right? So the time complexity. If we want to access the first or the last node, it is big O of 1. If we need to perform insertion or removal at any known position, again it is big O of 1. But if you want to access the element by index, so we need to traverse the list up to that point. So it becomes big O of n. When to use list? Frequent insertions and deletions at any arbitrary position in the sequence. The elements are large or expensive to copy or move, so you do want to avoid vectors reallocation cost. And you need stable iterators. So basically, whenever you have to perform frequent insertions and deletions at random positions, then lists are more useful. Okay, so to use a list, we need to include the header file list. Again, to use a list, we need to define the data type, that which type of element we want to store in the list. Now, we can iterate over list by using two ways, either by range-based loops or by using the iterators. If we are using the range-based loop, these are the most efficient way. So, if we are using the range-based loop, we do it something like this. On the other hand, if we are using the iterators, again we are defining a list with some elements. For iterators, we need to define an iterator on that list, which will begin from first element, will go up to the end, which is the last element, and then you use the iterator to print the value. We generally use the iterators when we modify the list as well as we iterate over the list. So if we are modifying as well as you are iterating over the list, then we use the iterators. Now, if we are going to compare vectors with list, as we said, vectors are dynamic arrays, whereas lists are dynamic linked lists. Memory layout, vectors are contiguous memories, whereas lists are non-contiguous. Memory overhead is low because we just need to maintain the capacity, but it has in list, it is high because with every node we are maintaining two additional pointers, one for the forward, one for the backward. Random access, vectors are randomly accessed. It takes big O of 1 complexity, whereas lists are big O of n for random access operations. Insertion and removal at end. Again, vectors takes big O of 1 time. List also takes big O of 1. If we need to perform insertion and removal of element in between of the container, it is big O of n, it is big O of 1. Cache friendliness, excellent. Poor. Iteration invalidation. On reallocation, just insert and erase only if elements are erased. Spatial operations, dot reserve, dot capacity, whereas list provides you some spatial operations like splice, merge, and sort. There are multiple operations which are provided by these containers. These are some real life situations for you that in what scenario what will happen. For example, building a list by appending. You need to insert, the task given to you is you need to insert 10 million integers with pushback. So you should use vector or you should use list. In that case, vector is the winner. Because if you are going to use insert by list, every time it will be big O of n complexity because you are inserting at n. List big O of 1 is slower due to the constant heap allocations for node. You need to, every time you need to create a heap allocation. Whereas lists are faster. Another case is frequent insertions in middle. You need to perform number of insertions in middle. In that case, lists are winner. Another case is you need to iterate and processing. Sum all elements in a container of 10 million integers. Then what you should use, either list or vector. Again, vector is winner. So vector is the by default general purpose container. It provides a fast access and iteration due to the cache coherence. List, on the other hand, is specialized for certain scenarios, like if we have to perform the insertions and deletions in middle. The choice depends on you, but generally we use vectors over the list. Okay, then we discuss about the next abstract data type, one of the most commonly used abstract data type, which is the stack. A stack is based on last in, first out, which means the element which is inserted last will be removed first. For example, if you stack number of books one on the top of other, this is one book, then this is other book, then this is other book, and this is other book. So whenever you are inserting the book, first you insert this book, then you insert this, then you insert this book, and then you insert this book. Number 4. When you need to take out the books, which book you will take first out? The number 4, the last book will be taken out first. Then number 3, then number 2, and then number 1. So this is the stack data structure. The data which is added last is removed first. It is again a linear data structure. Elements are arranged in a linear manner. All elements should be of same type. Adding the elements to a stack is called as the push operation, whereas removing the element from the stack is called as the pop operation. These are some of the operations, common operations of a stack. Push, inserting the element at the top of the stack. Pop, removes the top element from the stack. Peek or top, it just returns the top reference of top element. It does not remove the top element, it just returns the reference of top element. Whereas pop removes the top element. Empty check, to just check whether the stack is empty or not. Size, the number of elements currently present in the stack. Real world applications of stack. Where do we use stack? The stacks are used in number of applications. Like we have covered recursion in the last week. Function call management. The call stack is maintained by the stack. In case of recursion, all the function calls are maintained by the stack. If we need to evaluate expression or it's a parsing, like whether if I'll say this 1 plus 2 times 3, is it a valid expression or not? So how you can check it? It can be checked by using a stack. If we need to evaluate a postfix expression where the operator is at the end of the operands, like this. This is the postfix expression for 1 times 2. So to evaluate postfix expression, we use the stack. If we need to perform the undo redo operations, again we use the stack because all your operations are pushed into the stack. And whenever you perform the undo operation, the last operation is executes. Back forward navigation in browsers, again all the URLs are stored temporarily in the stack. Depth first search, when we talk about the trees, it's a traversal algorithm. We use BFS and DFS, breadth first search and depth first search. So in case of depth first search, we uses the stack, whereas in case of BFS, we uses the queue. These both are the graph traversal algorithms. In case of DFS, we uses the queues. Complexity analysis. All the core operations like push, pop, top, empty are big O of 1. Space complexity, big O of n, where n is the number of elements stored, that what is the size of the array. Overhead, if we, again, the stacks can be implemented by two ways, either by using the arrays or by using a linked list. If we are implementing stack by arrays, then the problem can be of the same of arrays, potential for unused allocated capacity. But if we are using a list-based implementation for a stack, then again we will need to store two extra pointers, one for the forward pointer, one for the next backward node, forward node and backward node. In that case, that will be the extra overhead of memory. Now, this is a demo code that how we use the stack. We need to include the header file .stack. We are using a string. We are going to implement a stack to store the history of URLs. Okay, so we are implementing a stack of type string, and the name of the stack is history. We are putting some values. We are pushing some values like google.com, github.com, stackoverflow.com. If we print the current site, since Stack Overflow, look, at the bottom is Google in the stack, then there is GitHub, then there is Stack Overflow, so the top of the stack is here. So if you print the current element, the top element, it will print Stack Overflow. Now, if you pop the element, so Stack Overflow is removed. So the top comes to the GitHub. So if you print the current element now, it will print the GitHub. Again, if the stack is not empty, is the stack empty? No. What is the current size of the stack? 2, because there are 2 entries in the stack. So it will print 2. The size will print 2. Now, while the stack is not empty, you print all the elements and remove those elements. So it should print GitHub and then Google. So this is a demo program for implementing the stacks, that how the stacks are implemented. So stack is a fundamental LIFO entity with critical operations for push, pop, top. It can be implemented using arrays, or it can be implemented using linked list. C++ provides a stack, std stack, as a container in which you can use. Big O of 1 operations makes it extremely efficient. It is indispensable for managing execution, call stack, parsing, and undo functionality. And always check empty before calling the pop or top to avoid undefined behavior. Like for example, if you are using the pop function on an empty stack, so it is an undefined behavior. So always you need to check the empty. If the stack is empty or not, only then you can perform the pop operation. Then next one is the QADT, Q abstract data type. Q is based on first in, first out operation. That means the element which is added first will be removed first from the container. For example, a checkout line. If a person is here, next one comes after this, next one comes after this, next one comes after this. If he got the ticket, it will be removed, then this one will be removed, then this one, and then this one. So the elements which are added in the sequence, the same sequence, they will be removed. So it is the first in, first out. It supports two primary operations like stack. In stack, we have push and pop operations. Here we call it as NQ and DQ operation. NQ, to insert an element at the end of the queue. If this is my queue, the elements are added from the backside. So NQ operation. DQ, the elements are removed from the beginning of operation, beginning of the container. NQ, to push the element. DQ, remove the element. Front gives you the first element, reference of first element. Back gives you the reference of last element. To check whether the stack queue is empty or not, we use the empty. To check how many number of elements are there, we use the size. Now, queue implementation, if we use the arrays for using the queue implementation, there is a problem of drifting array problem. What is that? For example, initial your queue is empty. We are having an array of 5 queue of 5, and initially the queue is empty. So my front is at 0 index, back is at 0. Always remember its index starts with 0. You push one element A, so front is 0, back is 1. You push one more element B, so front is 0, back is 2. You pop one element, so A is removed. So front is at 1, back is at 2. Now you push C, so it becomes B and C. Front is at 1, back is at 3 index. You again pop C. Front is 2, back is 3. Now, if we are inserting, suppose I am inserting one more element push. So it is inserted at position D. And if I perform one more push, it is position D. So my back reaches at the end of the queue. So by definition, queue is full. But we have some unused memory space here. So this is called as drifting array problem. To solve this problem, the queue is implemented as a circular buffer. Circular buffer where we check if elements are removed from the beginning. So if array is full at the end, the queue is full at the end, then we start back at the beginning. We start inserting the elements at the beginning in the circular manner. For example, if you see in this line, D is the last element. So we again start inserting elements at the beginning, and we use it to check we use this formula to calculate the next index. That what is the next index of the available index? What is the next index to insert an element? Queues again can be implemented by using a array or by using a linked list. So either we use this circular buffer solution if we are using the array, or we can use the linked list. So it avoids the problem of drifting array. Again, we have a 2 pointers here. One is the head. If this is my linked list to implement the queue, this is the head node. And this is the tail node. The last node is called as tail node, which points to the back node. So whenever you need to insert one more element, you will insert at the tail position. And whenever you need to perform the DQ operation, that is you want to remove the element, you will perform from the head position. So it is easy since you do not need to define any capacity. No drifting logic or no problem of finding the next index is there. So it is easier to implement because it is dynamic in nature. But the problem is again, you need to implement two additional pointers at every node, which is a memory overhead. C++ again provides a STL queue, which is the std queue, which we have in the queue header file. We use this syntax to implement the queue. Real-world applications of queues. We use queues in number of applications, like we use in task scheduling, data buffering, which is the producer-consumer problem, breadth first search, as I told you in a stack. In a stack, we use the stack we use in DFS, and queue we use in the BFS, breadth first search, which are the graph traversal algorithms. Messaging systems, nowadays we use RabbitMQ, Kafka, these queue-based architectures we use in the DevOps. So that is the messaging system. There we use the queues. Event handling in the GUI processes. So queues are applications of queues are a lot. Variations of queues. We have the double-ended queue, which are also called as DQ. Double-ended queue, in which we can perform the insertion and removal of elements from both ends. Unlike the normal queues, in the queues, insertions can be done at the back and removal of elements can be done from the beginning. But in double-ended queue, insertion and deletions both can be done from the both ends. So the operations push front, push back, pop back. Priority queues, where elements are dequeued based on a priority, not by their arrival time. So each element has an associated priority with it, and the removal of elements is done with their priority, with the associated priority. We use it in the CPU scheduling, the Jasper algorithm, and there are number of other algorithms are there. We use the priority queue. Complexity analysis, again, queues are one of efficient data structure. It push, pop, front, empty, all these takes big O of 1. Space complexity is big O of n, where n is the number of elements stored. Overhead, if we are implementing it using array, then the problem of circular buffer will be there. If you are using it as a linked list, then the overhead of extra pointers to store the address of next node and previous node will be there. Okay, this is very small, so we can do it later on. Okay, so Q is a fundamental FIFO additive with core operations push, pop, DQ, front, back. It can be implemented using a circular buffer or a linked list. In C++, we are having a stdq as a container. Big O of one operations make it a deal. So big O of one operation makes it ideal for buffering and ordered processing. And it is critical for scheduling like BFS and producer consumer systems. And yes, queues are not thread safe by default, so always try to have external synchronization whenever you are using the concurrent programming. Right. Now, let us talk about the tree data structure. List, vector, stack, and queues all are the linear data structures. Tree, on the other hand, is a non-linear or a hierarchical data structure, which consists of some nodes and some edges. The topmost node is called as the root. It has a parent-child relationship. A node is connected to other node below it. Leaf node, if a node does not have any child, it is called as a leaf node. Subtree is a tree within a tree. Depth, number of edges from the root to the node. And height is the number of edges from the node to the deepest leaf. For example, this is a tree. The root node, the topmost node, is called as the root of the tree. Edges are, these are the edges which are connecting the nodes. 15 and 25 are the child of 10. 2, 7, 6 are the child of 15. 9 is the child of 25. Or 25 is the parent of 9. Since 5, 12 and 9 does not have any child, so these are called as leaf nodes. 15 has child, 7 has child, 25 has child, 10 has child. So these are called as non-leaf nodes. 2, 7, 6 are the siblings because their parent is same. 15 and 25 are sibling. Depth is the number of edges from the root to the node. For example, if I'll say the depth of 9 is 2 because there are 2 edges. The depth of 25 is 1. And height of the tree is number of edges from the node to the deepest leaf. Like if I say that what is the height of the tree? So it is 1, 2, 3. The height of the tree is 1 because the maximum number of edges to that node. So it is the 3. And a tree within a tree is called as a subtree. So this is a subtree because it in itself it is a tree. If we talk about a binary tree in which each node can have at most 2 children. One is left children and one is right children. That is called as a binary tree. Binary search tree where binary search tree have a specific ordering property. The value of, if this is root, this is left node and this is right node. The value of left node will be less than the root node, that is the top node, root node, and the value of root node will be less than the right node. Or we can say it should be something like this, like it is 1, 3, 5. 1 is less than 3, 3 is less than 5. It cannot be like this, like 7, 3, 5. left node is always less than parent node, and parent node is always less than right node. The value of parent node is always less than the value of right node. If this property is maintained throughout the tree, it is called as binary search tree. Binary search tree enables us for most efficient searching operations basically. Tree traversal algorithms. Tree traversal algorithms. If we traverse the tree in the sequence of left node, left subtree, then node, then right subtree, then it is called as left in order. Pre-order, if node, then left subtree, then right subtree. Post order, left subtree, right subtree, node. For example, let us say we are having a binary search tree like this. It's 1, 3, 5, 7, 9. It is a binary search tree because in everywhere the value of left subtree is less than the node, parent node, and the value of parent node is less than the right subtree. Now, if we have to perform the in order is left subtree, then node, then right subtree. So it will be 1, 3, 5, 7, 9. If we need to perform the pre-order traversal, the pre-order is node, left, right. So node, 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 then left, then right, and then right. And if we have to perform the post order traversal is left subtree, right subtree, and then road. So it will be 1, 5, 3, 9, 7. And label order is the breadth first, visit nodes label by label. So it will be the label order will be 7, 3, 9, 1, 5. So these are the different traversal algorithms for a tree. Then we'll talk about the balanced binary tree. Balanced trees, or which are also called as the AVL tree. A problem with balanced BST, that is the binary search tree, is it becomes unbalanced. For example, if my tree is something like this, only left childs are there are no right child. So it is a unbalanced because only it is increasing in one direction, which is the left direction, but it is not increasing in the right direction. So for such trees, we use the self-balancing trees. Self-balancing trees, either AVL tree or red-black tree. AVL trees maintains a balance factor, that height of the left subtree minus height of the right subtree for each node, which must be either -1, 0, or 1. If an insertion or deletion violates these properties, we perform some rotations to make the tree balance. So height is always big O of log n, guaranteeing big O of log n time for core operations. Implementing a BST in C++, it is simply a structure that how we perform the code, write the code for tree. So we need to define a node first of all, in which we need to define, we are implementing this tree by using a linked list. So the left node and right node. The left node will hold the address of left child and right node will hold the address of right child. It is something like this. Like it is the value is 1 here, the value is 3 here, the value is 5 here. So this will hold the address of this node and this will hold the address of this node. Now for example, if you are having one more, I am having here value 4 and I am having a value of here 7 here. Then it will hold the address of this node, it will hold the address of this node. And since these are the leaf nodes, so there will be a null. So for each node, we need to define the structure something like this. The data which will hold the value, node pointer left, node pointer right. The node pointer which will hold the address of next left node and the node pointer which will hold the address of right node. Then we are defining a BST class in which we are defining the address of root node. And we are writing the code to insert the element in a tree, like inserting the element. So this is a simply skeleton to insert for a tree code. Applications of trees, since trees are hierarchical data structure, so if we need to implement the file system, our directory structure, if you see our directory structure, folder structures in our computers, laptops is hierarchical. So trees are used to store those hierarchy directory structure. Domain name system, that google.com, then inside that another domain, then inside that another domain. So that structure again is going to be stored by tree. Compilers, parsing the trees, abstract syntax, checking it all. So trees are used in compilers also. Decision trees, whenever you need to make a decision that whether to use this part or use this part, this part or this part. Whenever we have to make the decisions, we use the decision trees. Or databases, whenever we perform the indexing on our database. So we use the B trees, B plus trees. So there are plenty of applications of trees. Well, if we are now we're discussing the complexity analysis of balanced binary search tree and unbalanced binary search tree. So if it is balanced, the search, insert, delete all takes big O of n. But if it is unbalanced, that is the worst case complexity, then all take big O of n. So big O of log n is definitely better than big O of n. Space complexity in both of the cases is big O of n, that is where n is the number of nodes in the tree. Then another data structure or another container is the set. Set is a data structure or a container which stores all the unique values. It does not allow you to store duplicate elements. If an element is already there and you try to insert that element again, it will not have any effect, but it will not be inserted again. So a set is a container which is required when you want to have unique elements, when uniqueness is required. So no duplicate elements are stored. It is associative in nature, so elements are referenced by their value, not by index or by key. These are generally sorted, so elements are always traversed in a sorted order. The set operations, core operations are insert to insert an element, find to search an element, erase to remove an element, and size to find out the number of elements in the set. This is a dummy code where we are defining a set, and if you see here 2 is inserted twice. Then we are inserting 3. We are finding the 5. But if we try to print all the elements by the enhanced for loop, it will print 1, 2, 3, 5, 8. So you see 2 is printed only once, not twice, and elements are printed in ascending order, in sorted order. Whether we have not performed any sorting here, but it is automatically printed in sorted order. So insertion order is not maintained in a set. Elements are by default ordered here. So applications of sets, whenever you want to remove duplicate elements, if you need to check membership test, like if this element belongs to a collection or not. we use by using set. Mathematical set operations like union, intersection, differences, all these can be implemented by using the set. Implementing data structures like graphs or adjacency list, we use the sets over there. Another abstract data type in C++ is a map. Map is a container which store elements by key value pair. The elements are stored in key value pair. That for each key there is an associated value over there. So elements are accessed by their key, not by the index again. Unique keys has to be unique. Values may be duplicate, but keys has to be unique. No two elements can have the same key. Often keys are stored and thus iterated in a sorted order. So generally keys are sorted. Map operations like insert key value, as we said, these are always stored in a key value pair. So you need to, whenever you're performing the insertion, you need to do it in a key value manner. Access, either you do map key or map add. So if you give the key, it will return the corresponding value. To check whether a particular key exists or not, we use the find. Erase to remove an entry from the map. Size to have the number of elements in the map. Applications of map in the caching for memoization, like of Fibonacci numbers and all. Frequency counting, you want to check that how many students with a name X exist in a class. So we use maps over there to check. For database indexing, for symbol tables, for configuration of your programs, key value, like username is this, password is this. If we need to perform some configuration settings, we use the again maps. So maps again has lots of properties. So all was this about the week 2, in which we covered vectors, list, stacks, queues, maps, trees, sets. Yes. Okay. So just go through it. If you have any issues, any problem, just connect with me. You can meet me in office hours also. Have a nice day. Thank you.